So this video will be about the group S3 and D3, the dihedral group. Okay, so since S3 will be a set with 3 elements, 1, 2, 3, the permutations here will be 3 factorial, okay, and that will make 6. It's easy for you to see that. Okay. We can make right away the list of the permutations, but I also want to see this group from the geometrical point of view. So if we have a triangle, okay, I'm going to call this 1, 2, and 3. Okay, so the very first thing that I can do to this triangle is not to touch the triangle. Okay, a very important thing, not to touch it. Okay, important operation in mathematics. Okay, so that would be 1, 2, 3. Okay, 1 goes to 1, 2 goes to 2, and 3 goes to 3. Okay. Now what I can do is I have 1, 2, 3, so I can do it. So now 1 will be 2, 2 will be 3, and 3 will be 1. So what I did was to rotate the triangle. Okay, I took this triangle and I rotated. Okay, 1. So instead of 3, now I have 1. So 3 is 1. Okay, so I'm going to call this one rotation, and I'm going to use the row 0, rotation 0, and I'm going to call this one rotation 1, row 1. Okay, now 1, 2, 3. The second rotation can be 1, 3, 1, 2. I'm going to call it rotation 2, not very original. Okay, so where 1 will be 3, right, 2 will be 1, and 3 will be 2. So another rotation. Okay, if you look at this one, I took one rotation from this one and then another one, a second rotation. Okay, in a certain way, a composition of rotations. Okay, and I call the first one row 0, this one row 1, and this one row 2. Okay, well, but we saw up there that there will be 6 permutations. Okay, so we still have some other permutations. Now, what I can do is I'm going to put another triangle here, 1, 2, 3. I'm going to give it a different name now. So imagine from this one, the identity, I'm going to call it the identity, and it is the identity. I'm going to keep 1 at its position, okay? Okay. And in a certain way, I'm going to use this. I want to go back here. I'm going to use this line as a symmetric line. So I'm going to switch 2 to 3 and 3 to 2. Okay, so I'm going to mirror. Okay, I'm going to mirror these two. So this was 2 and this was 3. So now I'm going to do 3 and 2. Okay, so 1 will be 1, 2 will be 3, and 3 will be 2. So since this is I'm mirroring the vertices, so I'm going to call this mu 1. Okay, so this will be mu 1. More or less I'm going to do the same operation now, but this time I'm going to keep 2. Okay, and this will be mirror 2. So this time I'm going to keep 2, and I'm going to switch 1 and 3 to mirror them through this line. Okay, so 3 goes to 1, 3 goes to 1, and 1 goes to 3. Okay, so 1 will be 3 and 3 will be 1. Okay, and by now you know what I'm doing, so the last one obviously is going to be the last possible mirror here. Switch 1 and 2. Okay, and keep 3. So the last one will be 1, 2, 3. So I'm going to keep 3. Okay, I'm going to call it mirror 3, and 1 will be 2 and 2 will be 1. So we'll have a 2, 1, 3. Okay, here we are. The 6 permutations of SC, the symmetrical group S3. 1, and this will be the identity. 2, 3, 4, 5, 6. Okay, and I'm going to keep these names. Now, let me use one of them that is not that obvious. For instance, R1 and R2. Okay, imagine I want to do an operation like R1 times R2. Okay, so I'm going to do as in the previous video. Okay, I have to put R1 first and R2 next. Okay, so it will be 1, 2, 3, 1, 2, 3. Okay, so R1 is 2, 3, 1, 2, 3, 1. R2 is 3, 1, 2, 3, 1, 2, and that will be 1, 2, 3. So let us pick up. Okay, for instance, 1. What is R1 of R2 of 1? It will be R1 of it will be R1, R2 of 1 goes to 3, right? So R1 of 3 is 1. Okay? So R1, so 1 goes to 1. Okay? And what is R1 times R2 of 2? It will be R1, R2 of 2 goes to 1. So R1 of 1 goes to 2. So 2 goes to 2. And it's really easy to check that R1 times R2 of 3 will be R1, R2 of 3 goes to 2, R1 of 2 goes to 3, and 3 goes to 3. So we can say that R1 times R2 equals R0. Okay? Because this is R1, right? 1, 2, 3, 2, 3, 1. 1, 2, 3, 2, 3, 1. This is R1. This is R2, 1, 2, 3, 3, 1, 2, R2, 1, 2, 3, 3, 1, 2. And when we made the composition for R1 times R2, we got R0. Okay, we got R0. Now, okay, this is the more challenging part of this, to make a table for this. Well, we can put R0, R1, R2, M1, M2, M3. The operation here is the composition of operations, and we put again R1, R0, R1, R2, M1, M2, M3. We saw that R0 is the identity, so R0 times R0 will be R0, R0 times R1, so this will be all the same, since this is the identity. The same here, okay, mirror 1, mirror 2, mirror 3. Now which one we made? We saw that R1 times R2 is R0, right? Okay, let's use that one. So R1 times R2, right, is R0. And now you have to go and check one by one. Okay, with a little experience, then you do it quickly. Okay, so I'm going to leave here for you guys to check. If you see any mistake in these videos, please let me know. Okay, it's obvious that I'm not going to do one by one, but if you have any problem with any one, just let me know, and we can make a video for that. M1 times R0 is M1. M1 times R1 will be M2. This is packed with regularities. Okay, you see, for instance, M1 and mu1, mu2, mu3, and then R0, R1, R2. This is packed with regularities. Okay, mu3, mu1, but you also have to be careful, okay, because this is not, it's not only, there is no order here. Okay, for instance, here is mu1, mu2, mu3, R0, R1, R2, but this is mu2, mu3, and then mu1. Okay, there are regularities, but not the expected ones. Okay, not what the first intuition dictates. If you are an absolute beginner, you do have to do all this. Okay, so this is the multiplication. I hope you guys can see well. So this is the multiplication table for S3. Okay, this is the multiplication table for the symmetric group 3. I want to call your attention that this group is not abelian, and we will talk about that later. Okay, and now I want to talk about these triangles. We made this. So the triangle is a 3-agon right? Okay, so we can say that there is a natural correspondence between the elements of S3 and the ways in which two copies of an equilateral triangle with vertices 1, 2 and 3 can be placed, one covering the other with vertices on top of vertices. That's what we did here. Okay? So for this reason, we say that S3 we can say that S3 is isomorphic to D3. Okay? We can say some other things too. I'm not going to say now, because we can say that S3 is isomorphic to D3, but we can also say for the more advanced viewers that it is the same as the semi-direct product of 3 times C2, because there is only one non-abelian group of order 2p for any odd prime p. But okay, but that's a lot for the moment. Okay, and what I want to say is that S3 is also the group D3. If you want, you can say they are isomorphic. S3 is also the group D3, and this is we call it group D3 of symmetries of an equilateral triangle. Okay? So D3, I'm going to write this because after this I'm going to move to the dihedral. So D3 stands for the third dihedral group. Okay? So the nth dihedral group, the notation is Dn, is the group of symmetries of the regular, do not forget regular, okay, the regular n-gun. Okay, so we considered S3 acting on the triangle. Okay, now that I'm here, I think I will move on to the D4. Okay, so I was thinking doing another video, but maybe since, well, if you watch this then you will understand everything. Okay, so the other group will be D4. Okay, D4 of permutations corresponding to the ways that two copies of a square, so now we are on a square with 1, 2, 3, 4, and now we are not in D3 anymore, we are not a dihedral group anymore, we are the D3, we are on D4 now. Okay, So 2 copies of a square with vertices 1, 2, 3, 4 can be placed, one covering the other, with vertices on top of vertices. Okay? So D4 will then be the group of symmetries of the square. Okay? Group of symmetries of the square. Okay? It's also called, I don't know if many of you are used to this, octic group. Okay, that's another name for this. Okay? So following the same idea as we did for the triangle, now we are going to have 1, 2, 3, 4, and this will be the identity. Okay, I'm going to call it 0. 1, 2, 3, 4, 2, 3, 4, 1 will be rotation 1. So here we have 1, 2, 3, 4. Here will be, so 2, 3, 4, 1. Okay? We have a rotation in this direction. Okay? Okay? 1 went to 4, 4 went to 3. You see? There was a rotation here. Now 1, 2, 3, 4. 3, 4, 1, 2. That will be second rotation. Okay. 3, 4, 1, 2. One rotation and another rotation. Okay. Looking at the first, you see 1 went to 3, 1 went to 3. You see, so there was a composition of rotations here. And finally we have 1, 2, 3, 4, rotation 3 will be 4, 1, 2, 3. Okay, so now this is 4, this is 1, this is 2, this is 3. So one rotation, another rotation, and another rotation. Okay, so 1 went here, and then went here. Okay. Okay. Next rotation will be the identity. Okay, so if you perform rotation 4 times, you get the identity. Okay. Okay, and we also have mirrors here. So 1, 2, 3, 4. I'm going to call it M1, 2. So 2, 1, 4, and 3. So I can mirror through this line. So 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. Okay, 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. Okay, so 2, 1, 4, 3. Okay, that's the mirror here. 1, 2, 3, 4. The second mirror, so mirror 2 will be 4, 3, 2, 1. Obviously 4 exchanges to 1 and 3 exchanges to 2. 1 to 4, 4 to 1, 2 to 3, 3 to 2. Okay? So 4, 3, 2, 1, and this is this mirror where they switch 1 and 4. Okay, now okay, we also have we can also mirror through the diagonal if you want. Okay, so that will be 3, 2, 1 and 4, meaning we had 1, 2, 3, 4, and we can keep 2 and 4. That's what we did here. We kept 2 and 4. Okay, so we had this diagonal, and we switched 1 and 3. 1 goes to 3 and 3 goes to 1. Okay, and I'm going to choose delta 1 for this. Okay, last one will be this line, obviously. 1, 2, 3, 4, where I keep 1 and I keep 3. So 1 and 3, 2 goes to 4 and 4 goes to 2. Okay, and that will be delta 2. Okay, I'm not going to even show it. I think you can go back and see that, for instance, if I do, for instance, these two, because I have them here. If I do delta 1 times delta 2, okay, delta 1 times delta 2, you can go and check, we'll get R2. Okay, let's do this one. Sorry, typical of me changing my mind every 5 seconds. Okay, sorry guys. Okay, delta 1 times delta 2 will be 1, 2, 3, 4. Okay, delta 2, 1 goes to 1 and 1 goes to 3, right? Okay, okay, 2 goes to 4, 2 goes to 4, and 4 goes to 4, so 2 goes to 4. 3 goes to 3 in delta 2, and 3 goes to 1 in delta 1. 4 goes to 2, and 2 goes to 2. So we have 3, 4, 1, 2. 3, 4, 1, 2. That's row 2. Okay, so the composition of delta 1 times delta 2, you get row 2. Okay. I hope I can do it now more or less. This is going to get big, so better to do it this way. So I need row 0, row 1, row 2, row 3. You can get this on Wikipedia, on so many books on algebra. Okay, delta 1 and delta 2. Okay, so row 0, row 1, row 2, row 3, mu1, mu2, delta 1, delta 2. Okay, this is the identity, so I'm going to get always the same. This is easy. Okay, you don't have to check, because any 1 times the identity, you get the same. So this one too. Delta 1, delta 2. And now I hope I'm not making any mistake here. R1, R2, R3, R0, delta 1, delta 2, mu 2, mu 1. If you guys see any mistake in this video, please let me know, okay? Now R2 times R0 we get 2, R2 times R1 we get R3, right? R0, R1, M2, M1, delta 2, delta 1. Okay, R0, R3, R3 times the identity, that's correct. R0, R1, R2, delta 2, delta 1, M1, M2. For mu1 we get mu1, delta 2, mu2, delta 1, R0, R2, R3, R1. Okay. Delta 1, mu1, delta 2, rho 2, rho 0, rho 1, rho 3. Rho 1, rho 3, rho 0, rho 2. Okay, and the last one, delta 2 times the identity, this will be M2, delta 2 times R1, yes, delta 1, M1, R3, R1, R2, R there. Okay.